Can we make bioplastics from invasive plants or wheat straw? Yes, we can. My name is Renata Bura. I'm on a faculty in the School of Environmental and Forest Sciences in the College of the Environment. I use nature to engineer carbon-neutral products such as jet fuel, biochemicals, and bioplastics. I even make them from waste materials, which is fantastic for the environment. Here is one example. In my lab, we use straw, canary grass, which is a invasive species, and hemp to produce bioplastics. The process is simple, inexpensive, uses low energy and low amount of water and non-toxic chemicals. We have even created a startup, Verdant Nanomaterials, based on our patent. I collaborate with environmental engineers, material scientists, and process engineers. I work with companies and communities. I would love to collaborate with anyone interested in producing sustainable biomaterials.
Hello, my name is Dichiara. I'm an associate professor in the School of Environmental and Forest Sciences. My background is in material science and nanotechnology, and I work within the Bioresource Science and Engineering program on developing sustainable alternatives to petroleum-based fuels, chemicals, and more specifically, electronic materials. My main research area focuses on all-carbon electronics from renewable waste and biomass feedstock using innovative processes that are both scalable, economically viable, and carbon neutral. My group can produce biocompatible, lightweight, and flexible fibrous materials with tailored characteristics in various form factors, such as filaments, papers, gels, or molded pulp. These structures can then be used in many different applications like harvesting energy from the human body and storing it in translucent capacitors to power sustainable resistive and capacitive sensors. I typically collaborate with chemical and electrical engineers as well as data scientists from diverse communities across the globe, and I would be very excited to work with UW researchers to expand the scope and develop a commercial avenue for our sustainable electronic product.
Hello, my name is Rick Gustafson. I'm on the faculty in the School of Environmental and Forest Sciences in the College of the Environment. I do process development research. This slide shows the kind of processes I developed. Here we take various feedstocks from invasive species to residuals and feed them to a factory that makes jet fuel, formic acid, and xylitol. We investigate technical feasibility, economic performance, and life cycle environmental impacts. In this process, we are able to make $3 per gallon jet fuel, and the fuel is net carbon negative. Both are great results. I collaborate with environmental engineers, material scientists, and chemists. I work with companies, and I work with communities such as Lewis County and the Squaxin Island tribes. I'd be very excited to work with UW researchers interested in developing a commercial process.
My name is Tomás Méndez Echenagucia, Assistant Professor in the Department of Architecture, and my presentation is Computational Design for Sustainable Construction. My work centers around energy, acoustics, and structure. For example, when I look at energy and structures, I try to reduce the embodied and operational carbon emissions of building structures and envelopes. When I look at acoustics and energy, I design acoustic metamaterials that can increase building ventilation while reducing noise indoors. And when looking at structure and acoustics, I study how to reduce the embodied carbon of acoustic noise reduction measures. As you can see, at the center of my work is reducing CO2 emissions. I employ large-scale prototyping, as well as using parametric modeling, computational geometry, multiphysics simulation, data visualization, digital fabrication, and machine learning. Thanks very much.
My name is Bart Nijssen, and I'm the chair of Civil and Environmental Engineering, or CEE, at UW Seattle. As a hydrologist, much of my research deals with the impacts of climate change on droughts, floods, snowpack, and streamflow. But I would like to focus on the role of my department. As civil and environmental engineers, we don't just replace our aging infrastructures. We shape and create the world of tomorrow. Given that the built environment is a dominant source of greenhouse gas emissions, we have an important role to play in combating the climate crisis. CEE faculty are leading efforts to prepare for a rapidly changing world and to design solutions that support an equitable future. We design smart transportation systems and sustainable infrastructure. We study coastal flooding, extreme events, and clean air and water. And we even look for ways to remove carbon from the atmosphere. As a faculty, we embrace emergent tools and technologies to enhance the well-being of our communities as we create resilience and sustainability in the built and natural environments.
Hi, I'm Cody Schlinker, Washington Research Foundation Innovation Associate Professor of Chemistry and Clean Energy. Rising energy demand, climate change, as well as resource equity and security continue to spur renewable energy innovation. Members of the Schlinker Group explore fundamental chemical principles with the potential to boost the power of existing solar panels, increase the usable lifetime of rechargeable batteries, and even use the energy of the sun to produce clean burning fuels such as hydrogen. For example, the Schlinker Group is developing new materials that can capture light that existing solar panels waste and upcycle the energy from this wasted light into a form that the solar panels can actually use. It's almost like finding a great deal at a thrift shop. Successfully transitioning our light conversion technology into the solar power market could dramatically reduce the cost of installing solar panels because the cost of labor, wiring, hardware, and permitting can actually be 50% or more of the system cost. This means that even if the panel is free, these other hidden costs can still be a financial barrier to going solar. Ongoing work in the Schlinker Group aims to boost the power output of the solar panel to offset these hidden costs, making it more affordable to install solar.
Today, I propose a new biological sink for nitrous oxide. Nitrous oxide is a greenhouse gas 300 times more potent than CO2, and most of humanity's nitrous oxide emissions come from fertilized agriculture, so about 70%. We will introduce the bacterial nitrous oxide reductase, into OR, into the mitochondria of plants. If this were done successfully, about 32% of global crops were engineered, annual increases of nitrous oxide in the atmosphere could be prevented. If all crops were transformed, half of the current annual CO2 increases could potentially be offset by losses of nitrous oxide as equivalent CO2, and this would slow global temperature increases.